All right, welcome back. Um, we have another question. If A, comma B is an element of R, where R is a set of real numbers, show whether or not the operation asterisk is commutative under A asterisk B equals A plus B plus AB. Solution. The binary operation is giving us A asterisk B, which is equals to A plus B and the question is actually to show if the operation asterisk is commutative. Remember that for a non-empty set which is closed under binary operation, the binary operation is said to be commutative if A asterisk B is equal to B asterisk A. For a non-empty set which is closed under binary operation, the binary operation is said to be commutative if only A asterisk B is equal to B asterisk A. Now we are given A asterisk B as A plus B plus AB. Now what is B asterisk A? B asterisk A will be equal to, now the first alphabet first, and what is the first alphabet, which is B, plus here, what is the second alphabet? And second alphabet is A, then plus the product of the first and the second, product of the first and second, which is plus BA. So here is A asterisk B, here is B asterisk A. Now, A asterisk B is A plus B plus AB. Let's equate it to B plus A plus BA. Is this operation commutative? Which means is the value by the left hand side equals to the value by the right hand side? The answer is yes. But let's check. Let's use 2 asterisk 3. So using 2 asterisk 3 for A asterisk B, which is 2 asterisk 3, will now be 2, which is the first, plus 3, which is the second, plus 2 times 3. Therefore, 2 asterisk 3 will now give us 5 plus 6. That makes 2 asterisk 3 to be equals to 11. Now, still using 2 and 3, let's interchange it as B asterisk A, which will now be what? 3 asterisk 2. So using 3 asterisk 2, what's 3 asterisk 2? 3, 2, then 3 times 2. 3 plus 2 plus 3 times 2. That gives 3 asterisk 2 to be 5 plus 6. So 3 asterisk 2 is equal to 11. Now you can see that 2 asterisk 3 is equal to 3 asterisk 2 under the binary operation A asterisk B equals A plus B plus AB. Therefore, the binary operation is said to be commutative. Alright, we have another question. The operation asterisk on the set R of real number is defined by x asterisk y, which is equal to x squared plus y squared minus 2xy. Is the binary operation commutative? That's the question. Solution. The binary operation is giving us x asterisk y to be equal to x squared plus y squared minus 2xy. And the question is this binary operation commutative? Recall that for a binary operation to be commutative, it therefore means that x asterisk y must be equal to y asterisk x. Now we already have x asterisk y. Now let's find y asterisk x. Therefore, y asterisk x will be equal to y squared, which is the first term, plus x squared, which is the second, then minus 2yx. Just like we have here, we just change the first term and the second term of what we have here. Now, we have x asterisk y, we also have y asterisk x. Is this commutative? And the answer is yes. Why? Because we have just addition and multiplication. So it is commutative. Well, let's check. Checking also, let's use 2 asterisk 3 and 3 asterisk 2 under this binary operation x squared plus y squared minus 2xy. So for 2 asterisk 3, it is the square of the first term, which is the square of 2, plus the square of the second term, which is the square of 3, then minus 2 times the product of the first term and the second term, which is the first term times the second term. So 2 asterisk 3 will be 4 plus 9 minus 2 times 3, 6. 6 times 2, 12. So 2 asterisk 3 will be 4 plus 9, that's 13 minus 12. So 2 asterisk 3 is equal to 1. Now let's check 3 asterisk 2. 3 asterisk 2 will give us the first square of the first term plus square of the second term minus 2 times the product of the first and second term. The square of the first term plus square of the second term minus 2 times the product of the first and second. So we have 3 asterisk 2 to be 9 plus 4 minus 3 times 2, 6. 6 times 2, 12. So 3 asterisk 2 will be equal to 9 plus 4, 13 minus 12. Therefore, 3 asterisk 2 is equal to 1. You can see that 3 asterisk 2 is equal to 1, 2 asterisk 3 is equal to 1. That means the binary operation has been confirmed to be commutative. Alright. For the last question we'll be looking at under commutative property is the operation asterisk on the set Q of rational number is defined by x plus y equals to x plus y minus 2x plus y squared. If x comma y is an element of Q, show whether or not the operation asterisk is commutative. So this is to show if the binary operation is commutative. Solution. The binary operation is given as x asterisk y equals x plus y minus 2x plus y squared. We have to show if this binary operation is commutative. And recall, we said the law of commutativity simply says that if x asterisk y is equal to y asterisk x, then the operation is said to be commutative. Now let's find y asterisk x. Y asterisk x will be equal to X asterisk y is x plus y, which is the first term plus the second term. So y asterisk x will be what? Y plus x. Then we have minus here, minus, then 2 times the first term. What is the first term? The first term here is y, here is x. So here we use minus 2y, then plus y squared. What is y squared? Y is the second term, which is square root of the second term. Here, our second term here is x. That will give us x squared. Now, is x asterisk y equal to y asterisk x? The answer is no. Therefore, this binary operation is not commutative. Let's check. Now, using 2 asterisk 3 and 3 asterisk 2 again. Now, we say 2 asterisk 3 is equal to x plus y, which is 2 plus 3, minus 2 times 2, which is the first term, times 2, then plus y square, which is the square of the second term, which is 3 square. So 2 asterisk 3 The binary operation asterisk is not commutative under x asterisk y equals x plus y minus 2x plus y squared.